Okay, let's go ahead and get started. Can anyone tell me, on Friday was the microphone off? Does anyone remember? Okay, so for some reason, the lecture capture doesn't have any audio on it. So I'm gonna try using this microphone today, and hopefully that helps with that. Today, there are office hours after class if anyone has questions about the problem set that's due on Wednesday. And yeah, other than that, today we're going to be talking about, we're going to introduce groups, which we're going to study for a majority of the course. And these are a set with an operation that we'll assume satisfies some properties. So I'll just say, in general, the field of algebra well, let's say, let's go even further out. So, modern mathematics, in general, obviously there's a lot of things that fall under this umbrella, but the two biggest areas of study are algebra and analysis. So courses that you might take in analysis would be real analysis, complex analysis. Calculus is kind of like a baby step towards analysis. And obviously we're in a course called abstract algebra, so we're falling into this camp in this class. And what you do in algebra is you typically assume you have a set. Let's call it S, and assume it has an operation. So something like addition or multiplication, but they'll just satisfy some abstract assumptions. So assume it has an operation satisfying your favorite axioms, so just some collection of axioms. And then see what you can learn about these sets from their operations. So, and then just see what happens. And sometimes you have more than one operation. So some examples that you may have seen before are fields. So these are a set together with two operations, and you assume many things about the operations like associativity and commutativity and things like that. So fields are an example. Vector spaces are another example. Vector spaces have, of course, the operation of vector addition, and then you also have scalar multiplication. And today we're going to see the example of groups. And groups are like a really, really stripped down version. So what you'll see is that we only have one operation and three axioms. So it's not a whole lot to work with. And there are algebraic structures that people look at that have even less structure than this. But this is a good starting place, because it turns out that even though you're not assuming much about groups, they're a very general type of thing, there's a lot that you can say, and there's a lot of richness to the study of groups. Okay, so let's go ahead and see the definition. And today, I'm going to define groups, and then we'll spend the entire rest of the time discussing examples. So some of these will be examples that you may have seen before, and some of them will be new sets that you may not have thought about before. Okay, so a group and they're usually denoted by G, is a non-empty set together with an operation. So it'll usually be denoted with like a multiplication symbol, and this takes in 2 elements of G and returns you something else from G. And it's usually called multiplication, that assigns each ordered pair say A comma B of elements of G another element of G and it's usually denoted A times B, or as an abbreviation, you can just, of course, write AB. And we'll assume it satisfies, so to be a group, it must satisfy, so G and the operation times must satisfy the following 3 axioms. So the first one is associativity. So we'll have that A, B multiplied together, and then times C. This is equal to A times BC for all A, B, and C in G. The second one is the identity. So there is an element, and it's usually denoted E in G, called the identity, such that A times E is equal to E times A, and that's all equal to A. So basically multiplying by E doesn't do anything to A for all A in G. And we will prove tomorrow or Wednesday that the identity is unique. So basically you cannot have 2 elements in your group that do this. And then the last axiom is inverses. So for each element A in your group, there is an element B in the group such that A times B, this is equal to B times A, and that's equal to the identity. So every element of G has something that we can multiply by it to get back to the identity. So, and again, on Wednesday, we will also prove that that inverses are unique. So for each A, there's actually a unique element B that does this. And for that reason, we'll usually denote B. So this is just notation. We'll call the inverse of A. We'll denote it by that. So this is sort of like, will be allowed, this will make, like, this notation will be allowed once we know that there's a unique inverse. Okay, are there questions about this definition? So I want to point out two things about this. So the first thing is that we did not assume commutativity. So what I mean by that is that it is not necessarily the case that AB is equal to BA for any A and B in the group G. So we may not be able to switch the order of multiplication. And if every pair of elements does commute, so in other words, for all A, B in G, we have AB is equal to BA. So if G does have this property, then the group is called abelian. And for abelian groups, we'll see as the semester goes on that we can say a lot about the structure of what abelian groups look like. And non-abelian groups are a lot more complicated. And then, okay, so this definition, I'll leave this visible, sorry. So the definition of a group may appear like very abstract and unfamiliar. I remember the first time I saw this definition, I felt like a deer caught in headlights. I was like, what am I looking at? Like, what even are these things? But you actually know a lot of examples of groups already. So I'm going to give you a few minutes to think about and discuss what examples of groups you might be able to come up with. And then we're going to spend the entire class just like looking at examples of groups. So I'll give you like 5 minutes. Okay, let's go ahead and discuss the examples. So, what examples of groups did you all come up with? Yeah.
I just like have a question.
Yeah.
So like the inverses,
Yeah.
can B equal A? That's possible or?
Yeah, okay. So this is a good question. So is it possible for an element to be its own inverse? Can anyone think of an example of a group where, yeah, I saw your hand first.
So if you're in a group of real numbers, the identity is 1, and so A times B is 1, and B times A is also 1.
Yeah, okay. So, yeah, the identity is always its own inverse. So that's one example. And I guess, okay, so this is like jumping ahead a little bit, but here's like another example of a group. Okay, I'm gonna hold off on that question because I don't want to like expose you to the full complexity of what can happen right now, because I feel like we can see some simple examples first to build intuition. But it is possible to have elements even not equal the identity that are their own inverse. Yeah.
Could you have like if the group is rational numbers without 0 and the element is -1?
Yeah, okay, so that's an example. So okay, so let's start there. So if we have the rational numbers, Q, so we know two operations on the rational numbers. We have addition and multiplication. So if we think about the rational numbers together with addition, this is a group. Okay, so we can think about the axioms. Addition is associative. The element 0 is the identity. And we have additive inverses, right? Like you can take negative of an element and add that to itself, and that will get you 0, which is the identity. So this is a group. If you look at the rational numbers together with multiplication, we run into a problem. So what is the problem? Yeah. Yeah, so in this group, now the identity is 1 because we're looking at multiplication. And we have an element 0, and there's nothing I can multiply 0 by to get back to 1. So 0 has no inverse. So what we can do to fix this is we'll just take 0 out. And that, together with multiplication, this will be a group. Okay, and in this group, so to answer the previous question, in this group you have the element -1, which is in, and okay, I'm going to also write down some notation. So this is usually written as Q star. So if you have a set that you have some usual notion of multiplication on, but it contains 0, then just excluding 0 is denoted by that set star. So Q star -1 is in Q star, and -1 times -1 is equal to 1, which is the identity. So this is another example of an element that's its own inverse. Yeah, and we'll see more examples. Okay, so these are our two examples so far, the rational numbers with addition and the rational numbers without 0 and multiplication. Are there other examples? Yeah. Yeah, okay, so this is another good example. So if we look at matrices, we might want to make a group of matrices with respect to multiplication, with matrix multiplication. But again, these will not always be invertible, right? So think back to linear algebra. What is a condition for a matrix to be invertible? Like what can you do to test the invertibility of a matrix? Yeah. So, okay, yeah, so we can look at the determinant. So if we have a matrix M, we can take det M, and recall that M is invertible if and only if the determinant of M is non-zero. Okay, so so if we exclude these matrices, then we will get a group, and it's called the general linear group. So we can look at, it's denoted like this, so GLN F, where F is any field. This is equal to the set of matrices A from all n by n matrices over F, such that the determinant of A is not equal to 0. And this is also a group. So maybe we can talk through some of the axioms. So we know that matrix multiplication is associative, and we also know that we have an identity element, right? The identity matrix. If we multiply any matrix by the identity matrix, we get back the original matrix. And this determinant condition has guaranteed that we have inverses. But there's one other thing that we should really check, and it's that if we have, let's say A and B in GLN F, that A times B is also in GLN F. So why is that? Yeah.
When we define group multiplication, it's an operation that takes two elements and
Yeah. Yeah, so we're definitely, out of this operation, we're definitely going to get an n by n matrix, right? Why do we know that that matrix has non-zero determinant? Yeah. Yeah, so the determinant function is multiplicative. So the determinant of AB is equal to det A times det B. So if both of det A and det B are non-zero, then so will the product det AB. Okay, good. So that's the general linear group. I'm going to say kind of a general class of examples that are similar to the first example that we saw. So fields with addition are always groups. So like examples you may know are the real numbers with addition are good. Obviously the rational numbers we already talked about, and also the complex numbers with addition are a group. And fields to the star, so taking out 0 with multiplication are groups. So these would be like R, we're taking out 0, so that's R star, and et cetera, like C star, and so on. What about vector spaces? Are these groups? Yeah. Yeah. What's the definition of a what? Okay, so a field, so like aside, a field. So this is like, this has a definition similar to the one of groups that we just saw, but it's a lot more involved. So a field is a set and it has 2 operations, and then there's like a bunch of assumptions about what the operations satisfy. So I'm not gonna like list all of them out, but if you wanna talk about that more, then we can. Just know that like R, Q, and C are examples. So a field is a set with 2 operations satisfying, and then there's like maybe 8 axioms. Okay, so for vector spaces, what operation are vector spaces groups with respect to? Yeah. Yeah, so vector spaces with vector addition are examples of groups. So that means like R to the n with the usual addition. Vector spaces consisting of functions with vector addition as defined for functions, and so on. Okay, did anyone come up with other examples of groups? Yeah. Okay, that's an interesting one. Okay, so we have the set containing 2 elements that are true and false, and the operation is OR, XOR. Okay. All right, the only way I'm going to be able to know if this is a group or not is to just write the multiplication table. So now is like a good time maybe to introduce multiplication tables. So we can make a table where along the top and the bottom you write all the elements of the group. So true and false and true and false. And then in the entries of the table you write what the product is. So true XOR true would be false, right? Yeah. And then true XOR false is true, and false XOR true is true, and false XOR false is false. Okay, so what is the identity in this group? Yeah, false is the identity. And then true is its own inverse. And false is its own inverse. Yeah, this looks like a group to me. So this is an example of a group. Is this group abelian? Yeah, so this one is abelian, and we can see that just from the table because false true is the same as true false. We get true in both cases. So this is abelian. And this is called a multiplication table. All right, other examples of groups that you all came up with? Yeah. Things that what? Permutations, yes, this is an excellent example. And I was about to say this is our first example of a non-abelian group, but I'm wrong because the general linear group is non-abelian because matrix multiplication doesn't always commute, right? So this one is non-abelian. Okay, so what are permutations? These are, so usually you fix a positive integer n, so we'll take n from z greater than 0. And then permutations are bijections from the set 1 up to n to the set 1 up to n. So you can think of them as just reordering n elements. It's like the ways of reordering n things. And this is a group with the operation of composition. So if you take composition of functions to be the operation, then you get a group. Would it help to do an example? So n equals 2 is like maybe a little bit too trivial. So let's look at the case when n is equal to 3. Let's list all of the bijections from 1, 2, 3 to 1, 2, 3. So I just need to send each element on the left to a distinct element on the right. And the identity in the group is going to be the one that just sends each element to itself. So if I have any other function and I compose it with this one, or if I compose this function with any other function, then I get that function back. So this is the identity. And then there are 5 other ones. So I'll just make some copies of this. So there are 3 that are called transpositions. And what these do is they switch 2 elements. So for example, I could switch 1 and 2, or I could and leave 3 alone. I could switch 1 and 3 and leave 2 alone, or I could switch 2 and 3 and leave 1 alone. And then there's going to be 2 more elements, and these just cycle the elements around. So, for example, I can send 1 to 2, 2 to 3, and then 3 to 1. Or I could do 1 to 3, 2 to 1, and 3 to 2. Okay, so those are the permutations on on 3 elements. So usually the notation for this is S sub n. So this group is called S3, this 6-element group. Other questions about this example? We will do a deep dive on permutation groups in a couple of weeks, because there's like a lot to say about them, and they're super important for a lot of reasons. Did anyone come up with other examples of groups? Yeah. Yeah, so you can have like symmetries of some object. And this can take place in any dimension, but like for one, maybe the simplest example is like if we're looking at a square in the plane, what can we do to this square to get back the square? We could flip it horizontally or vertically. So we have like the horizontal flip. We have the horizontal flip, or sorry, the vertical flip. And then we could also rotate it in a number of ways. So you could rotate it like 90 degrees. There's like 180 degrees, and so on. So all of these different operations that you can do to the square that just get you back a square, those are the symmetries of a square, and that gives you a group as well. And then, yeah, the identity element would be just like leaving the square alone, so doing nothing. I'm just going to look really quick to see if I missed any important examples. Okay, yeah, there are a couple I want to talk about. So the set, and this will be denoted Zn, of the numbers 0 up to n minus 1, with respect to addition mod n. Okay, so this is a group. So the identity is 0. And you can figure out what the additive inverse of each element is by kind of taking negative of that number and figuring out what that is mod n. So this is called the integers mod n, and this is a group. Okay, and then there's one last example that comes up quite often. So our last example of a group is for each n greater than 1, we're going to define u of n to be the set of positive integers less than n that are relatively prime to n, And then this is a group with multiplication. Mod n. And you'll see in the problem set why we need this relatively prime condition. So the problem set will ask you to consider just all numbers less than or equal to n, and you'll show that that's a group with multiplication mod n if and only if n is prime. Yeah. Okay, yeah. So let's talk about mod n. So what does this mean? So if I have, let's say a is any integer and n is a positive integer, then a mod n is equal to the remainder on division by n. So this is like some number between 0 and n minus 1. So let's just do some examples. So like like 6 mod 2 is 0 because 2 divides 6. 5 mod 2 is 1. So similarly, like any even number mod 2 will be 0, and any odd number mod 2 will be 1. And then a property about modular arithmetic that might be useful. So if you have like a plus b mod n, this is equal to, this is the same thing as like first doing a mod n, then doing b mod n, and then modding the entire thing by n. And you can verify that if you'd like, but this is like useful, and the same thing works for multiplication. Okay, so with the last few minutes, let's look at one of these U groups a little bit more closely. So let's look at U10. So the elements of this group are all the numbers all positive integers that are less than 10 that are relatively prime to 10. So 1 is relatively prime to 10. 2 is not relatively prime to 10. 3 is. 4 is not because they have a common factor of 2. 5 divides 10, so those are not relatively prime. 6, again, is even. 7 is in this. 8 is even, so that's out. And then we also have 9. So this is a group containing 4 elements. And we can write down the multiplication table, which will also just be helpful for getting some practice with modular arithmetic. So okay, so 1 is the multiplicative identity. So just looking at this first column, we're going to get back 1 times 1 is 1, 3 times 1 is 3. We get 7, and we get 9, and same thing going across. All right, then 3 times 3 is 9, and that's in the set, so we're happy. 3 times 7 is 21. And what is that mod 10? 1, yeah. So we take out all the factors of 10 and we just get back 1. So that means that 3 and 7 are multiplicative inverses. So we'll get the same thing over here. What about 7 times 7? 9, yeah. And then 3 times 9, we'll get okay. I was like, I just did that multiplication wrong. Okay, so this will be 7. And then what is 7 times 9? 63? I guess we better get 3 in this column, so we get 3 here, and then 9 times 9 is 81. Okay, so this is the multiplication table for this group, and you can see every element has an inverse, so we're happy. We have a 1 in every row and every column. And I guess we expected this group to be abelian because we know that multiplication is commutative, but you can also see it in this table because it's symmetric across the diagonal. So looking at this, we have that symmetry, so this is abelian. Okay, so that was almost all of my examples, and I liked the ones that you all came up with as well. There are a ton of examples also listed in the book and elsewhere. So as you saw today, groups come in a lot of forms and have like a lot of different shapes and sizes and different properties. So this is going to be something that we're going to explore for many weeks to come. And on Wednesday, I'm going to talk a little bit about general proof techniques, and we'll use elementary properties of groups as examples. So we'll look closely at those proofs and how to do them. And then on Friday, we'll talk about something called the order of a group and subgroups. So I'll see you all then. My God. Bean, what is this? Yeah, can you show me?
Yeah. I guess I said that, like, for the problem, like, these two are less prime, and then you could say 7 plus 4 breaks up into 5 plus 3, 2 plus 1.
So wait,
and then,
we're proving. Wait, but you want to prove that these two are relatively common, right?
yeah.
So why? So you don't know necessarily that SMT exists.
You don't.